Okay guys, welcome to another weekly LeetCode solution walkthrough. My name is San Pham, and today we're going to walk through contest 390. As you can see that the contest is still ongoing. There's still 40 minutes left as the time of this recording, and I already solved all the 4 questions, so I might as well spend some time recording a solution for this one. Once again, these guys are so fast. Hopefully one day I will be as fast as these guys. My total time is 38 minutes, which is not bad, but these guys are way too fast. So hopefully I will be faster to improve my ranking next time. Back to the problems. So I think for this contest, the 4 problems are actually not very difficult compared to the last one where we have Dylan index and maximum K coins, which is way more gnarly. And it is really about being very careful with tracking so that you don't mess up and incur the 5 minutes penalty. This seems to be the theme of this context. This is what it's about. So the 2 more interesting problems for this contest is the 3rd and the 4th problem, the most frequent IDs and the longest common suffix queries. So let's go to the most frequent IDs. Basically, for this problem, and please pause the window to read the problem. I assume that when you come to this video, you already kind of read this problem already. If you have not, please pause the video. But essentially, what we have to do in here is that we have a bunch of numbers and a bunch of frequency. These are IDs. And every time we go through each number, we will update a dictionary that keeps tracks of the ID and the frequency. Now, sometimes we add more, so 3 means we add more, but sometimes we also remove, right? So 2 appears against here, but we'll remove 3 frequency from the results. So it doesn't always increase, sometimes it's decreased as well. And we actually have to be based on the frequency of the appearance of the ID, we have to return the most frequent ID in the collection at that time, right? So you can see here, so at step 0, we have 3 IDs. So we set answer 0 equals 3, which is okay, because we literally add 3 of IDs 2 in. So right now, ID 2 is the most frequent, right? Now, at step 1, we have 3 IDs with value 2 and 2 IDs with value 3. I think the way they do it is a little bit wrong. So ID 3 has value 2 and ID 2 has value 3. That's more accurate. So because 3 is bigger, answer equals 3. Now for step 2, right, we have 2 IDs, so ID 2 with value 3, so answer equals 2 because we remove the 3 frequency, the 3 times appearance of ID 2 already, so we only have 3 with 2 left. And then in the final step, we add ID 1 with frequency 1, so now we have ID 1 of frequency 1 and ID 2 of frequency 3. So answer is 2. So here are the outputs. I think this problem is actually kind of straightforward. So basically, what you have to do for this one is to keep track of the dictionary of counting, which would be pretty simple, right? So you have ID and also the count. But at the same time, every time we update this ID, we will change the count, right? So really the trick of this problem is how to actually find this count, like the highest count, in a very efficient time. Either you track the max count in a very efficient time, or you try to find the count in a very efficient time. Because if you don't find the count in efficient time, you will have the 10 to the 5th different IDs to search for, and if you search for like 10 to the 5th ID, then that's a problem because you have like an O of n squared problem, which will certainly time out for sure. So the trick to do that, or at least how I do it, would be that I actually keep track of something separate, dcount, where it is actually count. The key is a count, and the value is actually the set of ID. So ID1, ID2 here. Now, first of all, like we already reduced the number of counts already by doing this. So if you try to find the maximum count of this is going to be faster. Furthermore, Python actually have a data structure called sorted dict, which actually keep this count sorted as well. I know that it is a binary tree that keep tracks of these count. So by doing this, every time you add a new count in, it is only log of n. So because we walked through n times, the frequency was add, or the ID was add, rather, we have like an n log n algorithms. So because the key is already sorted, the count's already sorted, we simply peek at the last key. Now, so I think this is a pretty specific knowledge. To my knowledge, LeetCode actually allows this data structure to be used. Is very useful. You can think of it as like a dictionary, but with the key sorted, where you sacrifice a little bit of the addition time, so it's a log n instead of 1, but then you have all the keys sorted. So if you want to use the sorted keys for something, then this data structure is really useful. If you don't like this, then you can also implement the binary search tree on your own as well, but I believe that sorted dict is actually a legal data structure in LeetCode context. Right, so let's kind of come back to this problem. So this is kind of my code here. Like, I think the tracking of it is very gnarly. We have a dictionary, we have the dcount, which is the count to the set of IDs. And I think the tracking is the part that we have to be very careful. So adding to the count is very easy, but tracking, so sort of like moving the ID in and out of the count based on using the count as a key is very difficult, because you have to, before and after the transformations, we have the previous count and the current count. We have to remove the ID from the previous count and add the ID from the current count. And sometimes we have to remove the count itself so that the sorted dict is correct. Otherwise, you don't want some kind of key that is really high, but then the set of IDs is empty, right? So have to be very careful about additions of new ID and removal of new ID. I recommend separate them into two different cases. And yeah, once you keep track of this correctly, then all that is left is just return that append. So you just like add like the key, or sorry, the count rather, that has the highest value. And to do that, you do a peak item of -1. Okay, so let's actually go to the next problem. So problem 4 is called longest common suffix queries. And once again, please pause the video to read the problem. But to summarize, essentially we have a word containers. And for every query, we have to find the shortest word that share the longest common suffix. For example, if your word is CD, so the longest common suffix is CD, because all these words share CD. And then among the words that share the longest common suffix, you select the shortest word. And in this case, we return 1 because BCD is the index of the word's container. Something more interesting is like XYZ, right? So XYZ, you can see that there's no words here that shares any common suffix. So the longest common suffix is actually considered a blank string. And for this case, you basically just return the shortest word out of them, which is also still 1, which is BCD. Right. Now, one more thing to note here is that if there are two strings that have the same length, we have to find the one that occurred earlier in the words container. And this is actually really important. This is actually a pretty decisive point. It sounds really benign, but it actually is a major optimization component here that potentially makes our algorithm a lot faster because of this. Okay, so overall the solution for this would be a try. So, but this try is the reverse try. It's not a prefix try that we are commonly used. You actually build a suffix try. So let me just kind of put the example here. So let's assume that these are the word that is in your screen, right? You will have to build a suffix try, and basically what it does is that the first node of the try is going to be a blank node, and then each of the children is accessed by an interdictionary using the character. But now we actually walk backwards. So here for ABCD we actually do D, C, B, A. So first we have D, then we have C, then we have B, then we have A, right? And these are the node. Now here is BCD, so also D, C, and B, so it is also here. Maybe this is not exactly a really good example. So DCBX. So DCBX would be here, where we have like a node called X here. Maybe we can add some other words. So let's say we add BAC in. So for BAC, you would do like a C. You do like an A, and then a C, right? Now, why do we use this data structure? Because when we search for a suffix, it's actually a pretty simple and straightforward tree traversal. Let's say your suffix is CD, as we have in the previous example. You simply just kind of traverse the tree here. Obviously, you also do it backward, right? So you go to D first, and you go to C here. Now, something really nice about this one is that you just the problem asks for longest common suffix, and basically what it means is that you just need to search as deep as possible. So let's say you have to search for something else like XCD, for example, right? So XCD, we go to D, we go to C, but then there's no X here. So simply CD, or this little node here, is the longest common suffix. And here we literally found the node of the tree that we accessed to. So now the problem requires us to return the index of the word and the index of the shortest word. So the next problem that we have to do is how to kind of store this, like sort of store this information efficiently. And essentially what it does is that every time we try to create a node, we also consider the word there, and then also store the index of the word itself. So we also store the very results of the shortest word that have the same particular suffix as well. So let me show you how to track it. So once again, let's say you have DCBA here. You go to word 0. So initially, you update at the node word 0. You go to D and also put 0 here. B, put 0 here, and then I'm sorry, D, C, put 0 here, B, put 0 here, and then A, sorry, put 0 here. Now we have BCD, right? So notice here that for the second word, every time we go here, we will compare with the current word. in terms of length and index. If it is shorter, then we replace it. And now notice, we come back to this point that if they have the same length, then we find the word that occurred earlier. So this just basically means that it is equal length, and we don't have to change the tracking, which is very efficient. So here is BCD. We go, this word has length 3, so we actually replace it. We also replace this one with 1, so it goes to D, go to C, and then we go, no, and then that's it. We're here. Now we don't replace this because BCD, it doesn't have A, so I'm just gonna sort of change this a little bit here. This looks like a D, so let me change it to an A here. So notice here that this word doesn't have an A, so we just stop here. So if any word happens to have A, B, C, D, so the entire word as a common suffix, we actually need to return word 0, right, instead of word 1. So this is just a very natural way to sort of track this. Now finally we have DCBX, so the index of that would be 2, so let's try to update it. So 2 is here, but 2 is not updated because this word is shorter, so you don't update it. Now you go to D, the word is still shorter, BCD is still shorter, so don't update it. This still shorter, B still shorter, but X you update to here. So you literally just need to so now that you built the tree, you notice that you literally just need to traverse the tree and then return the answer. So let's just kind of see this in actions by pasting a few queries here. So here we have C, D, so we walk D and C. DC we return 1. Now BCD, so D, C, B you also return 1. And then XYZ you return 1 here, because XYZ there's no string that have any common suffix, so the suffix is considered blank, and we just return 1. And hey, the output is 1 here, so it's accurate. We actually do need all these optimization here, because it actually matters a lot in terms of time complexity. So notice here that we have 10 to the 4th words, and the length is actually pretty long. It's also roughly 10 to the 4th in terms of length as well. So the building of the tree itself is already roughly 10 to the 8th, right? We have like an O of n k, where n is like 10 to the 4th, and k is also roughly 10 to the 4th, so it's 10 to the 8th, which is acceptable. Now notice here that the storage as an index is very important. You might ask yourself like, hey, why don't I just store the word? The problem is that the word itself is also pretty long as well. The word is also 10 to the 4th. So if you store also like the words as well, and in the worst case scenario where the try are all different from each other, like every single word is like triggering a new notes, you end up with situations where the storage is just too much. So if you add like n, k, and l, which is like, that would be like a 10 to the 12th, and 10 to the 12th is generally not acceptable solution in LeetCode, and that will time out. So it's actually very important that you keep track of it as an index here. And then now we go to the queries. So we also have 10 to the 4th queries, and you also have this amount of lengths. So that would be another 10 to the 8th. 10 to the 8th for the tree traversal. So as long as you stay below 10 to the 9th, then most algorithms will not time out. This is usually like, you can think of it as like a computational boundary, because one operation tends to take 1 nanosecond in the CPU. So as long as your algorithm stay roughly below 10 to the 9th, then you can feel safe that it will not time out. So yeah, I think that's the overall solution. Once again, build a try using the suffix, and also search the suffix as deep as possible using the same try, and then make sure you do track by the index itself instead of the wording. and then make sure that we only store the earliest one, so don't overwrite it. And also don't store like an array of words, because there's no reason to. You only care about the shortest and earliest one, right? So don't store like the words, because otherwise this storage will blow up as well. So very important that you only store one index here. So the code for this problem is actually quite simple. We have the try. I store the word index. Usually for try, I like to have a get add node and a get node. So get add node means that you traverse and you also add the node as we traverse. I found this to be very efficient when I do contests. And then I also have the add word here. Notice that for add words, I put in the reference to the list itself and also the index, right? So if there's no word, then I assign the index, but then if there is already a word index, then I only assign it if the index is actually shorter. So that's how I add the word here. And then during the query step, it is really just a matter of traversing as deep as possible until you break, and then you append the word index. So yeah, that is the contest. Good luck. I think this is a pretty good exercise, though I don't think it is quite as good and as challenging as the Dylan index the last time. But best wishes to you guys. Cheers. Happy LeetCode.